Do you think the universe has existed eternally? Wrong. Scientists have discovered that our world might just be a quantum deception emerging from absolute nothingness. The ultimate puzzle humanity has pondered for millions of years. Where does everything come from? When Newton used the law of gravity to unlock the universe's door, when cosmic microwave background radiation illuminated the moment of creation, we realized that the universe's origin is more terrifying than nothing. It's a beginning where even time and space didn't exist. Physicists say the universe is a bubble born from zero energy. Philosophers question the linguistic paradox of something from nothing, and Hawking even declared that we're just a small bubble in the ocean of the multiverse. When the first Homo sapiens looked up, humanity's longing for the starry sky became irrepressible. They questioned why they existed, with an ancient question rising in their hearts. Where does everything come from? This question has accompanied human history, spanning the rise and fall of civilizations. In some hearts, it became myth. In others' hands, it was written into religion, all to touch that mystery. Generation after generation of wise men and elders continuously explored the meaning of existence and thoughts of consciousness. Until science arrived, human understanding began to transform completely. The contemplation of why we are here shifted from temples to the lenses of telescopes and microscopes, continuing to burn. Isaac Newton declared that natural laws must truly be universal. The law of gravity that makes apples fall to the ground also pulls the moon, making it orbit the Earth. He pointed out that natural laws apply not only here, but extend to every corner of the universe. This is a universe orchestrated by laws, precise and cold like clockwork, requiring no gods or monsters to drive the stars. However, it was precisely this precise and cold picture, a universe without will or purpose, that made many people feel deeply unsettled. Despite this, science continued to advance. Astronomers raised their telescopes, penetrating the night sky, revealing our Milky Way, a cosmic island with hundreds of billions of stars. They further discovered that our galaxy is just one among trillions of galaxies, and the universe is so vast it's almost unimaginable. Yet even so, the deepest question remained unresolved. Where does all this come from? And where will it go? Perhaps the universe never truly began. Perhaps it has always existed, forever existing, oscillating between being and nothingness like tides. Or perhaps nothing truly exists at all, and the universe only appears to exist for a while, brief and hazy like a dream. But these poetic speculations were rejected by the laws of science itself. In the 19th century, thermodynamics emerged, writing a cruel fate for the universe. In the rules of efficiency and energy flow, we first realized that entropy increase is a fundamental property of the universe's operation. Everything moves toward disorder. Stars will extinguish, mountains will erode, and even the entire universe will eventually reach equilibrium and death. So if the universe truly exists eternally, why isn't it now a complete chaos and sea of entropy? Why is there still order, stars, and life? This question deeply pierced the illusion of an eternal universe. In the 20th century, everything began to change, like some long-buried flower of wisdom suddenly blooming at a certain moment in time. A new generation of telescopes swept across the sky, pushing human vision from the dust beneath our feet to billions of light-years away. The greatest minds focused on one question: how does the universe work? From quantum fluctuations in the subatomic world to the gravitational dance between galaxies, mysteries were solved one by one. The night that once filled us with awe when we looked up began to reveal its structure and logic. Finally, we seemed to touch the edge of that age-old question: where does the universe come from? On June 20th, 1966, Georges Lemaitre died at the age of 71. In his final moments, he was gratified to learn of a strange new discovery. The entire sky was shining with microwave background radiation from the depths of space. When he heard this news, he smiled. He knew he was right. He had boldly declared that the universe had a beginning, a moment of creation. Now there was finally evidence. Lemaitre was a brilliant mathematician. In the 1920s, he was the first to apply Einstein's relativity to the universe as a whole, piecing together the blueprint of modern cosmology. Einstein had firmly believed the universe was eternally static, But Lemaitre saw a different cosmic fate in Hubble's observations. Galaxies were receding, the universe was expanding. Since it was growing larger, it must have once been smaller. Lemaitre used mathematics to trace back the universe's history until all matter and energy were compressed into a primeval atom. This was the moment of the universe's birth. This theory was initially ridiculed. In 1949, Hoyle contemptuously called it the Big Bang, never expecting this name to persist to this day. But more and more evidence emerged. Astronomers realized that if the universe had indeed been hot and dense, its afterglow should still remain in today's sky. So they searched for this relic radiation. Finally, in 1965, an antenna in New Jersey captured that indelible hiss, the cosmic microwave background radiation from the entire sky, the afterglow of the universe's initial fireball. At this moment, Lemaitre's theory was finally validated. He couldn't witness this victory with his own eyes, but at the end of his life, he already knew that the universe had a beginning, a day of creation, a day without yesterday. And this discovery brought cosmology to an even more profound question. If the universe really had a beginning, where did it come from? Modern cosmology is a glorious history of victories. It depicts how the universe evolved from fiery chaos to star-filled skies, explaining the miraculous evolution from the first few seconds to millions of years. But shockingly, it still cannot explain how the universe was born. We know the universe is expanding, cooling, and evolving, but where did it come from? This is the ultimate question that modern science still cannot answer. The reason is that modern physics itself is in the midst of a century-long schism. The two main protagonists of this schism. One is Einstein's general relativity, which precisely describes gravity, the curvature of space-time, and the fate of galaxies. The other is quantum mechanics, which reveals the probabilistic rules of atoms, particles, and waves. Both theories are extremely successful, but mathematically incompatible, fundamentally unable to coexist. Usually, scientists can choose one. Either study cosmic-scale objects or microscopic particles, keeping them separate. But when we try to understand the moment of the universe's birth, problems arise. At that time, the universe was at an extremely small scale dominated by quantum gravity, yet possessed extremely high energy density, with space-time severely curved and quantum fluctuations surging incessantly. At that primordial moment, the schism between relativity and quantum mechanics could no longer be avoided. Physicists believe that in that chaotic initial moment, there existed a unified force, a superforce, a cosmic source transcending all known natural forces. As the universe expanded and cooled, this superforce split into the familiar gravity, electromagnetic force, strong nuclear force, and weak nuclear force. But at that initial moment, they were unified. Understanding this primordial force would unlock the mystery of the universe's emergence from nothing. Thus, physicists embarked on the quest for a theory of everything. String theory, supersymmetry, extra dimensions, loop quantum gravity theories were born and theories fell. A century has passed, and the theory of everything remains elusive. Without it, our mathematics cannot penetrate the ultimate veil of time, cannot cross the Planck wall of 10 to the power of -43 seconds, and thus cannot see the true scene of creation. So today, although we can simulate the birth of galaxies and recreate how the first light illuminated the darkness, we still cannot answer that most fundamental question. How did the universe begin? Perhaps our story has reached a boundary. We stand before the maze of mathematics, our brightest minds trying to crack the universe's ultimate code, searching for the key to unlock the door of ignorance. But the question is, what will be behind the door? If we could really trace back to the end of time, back to the universe's initial moment, what would we find? Some physicists give a disturbing answer. At that starting point, temperature and density approach infinity. All time, space, matter, and light are compressed into a point, a singularity. And before that, there was nothing. Not empty space, but no space. Not very early time, but no time. This is true nothing. No space, no time, no dimensions, no existence. But this is exactly what's confusing. If there was nothing, how could there be a universe? If there was no space, where did the explosion occur? If there was no time, when did evolution begin? We don't even have a reference point to describe this transformation from nothing. This is the boundary of physics and the territory of philosophy. Here, science and philosophy often clash. Physicists say we can measure, deduce, and model. Philosophers counter. When you describe nothing, doesn't the language you use already assume something? What does nothing actually mean? Empty space? Vacuum energy waiting to be awakened? Or doesn't even emptiness exist? It's precisely in this ambiguous zone that a series of bold theories have been proposed. Some say the universe spontaneously emerged from quantum fluctuations, like bubbles from nothing, where a single vacuum fluctuation gave birth to the entire world. Others say the universe arose from collisions of membranes in higher dimensional space, and were just ripples in an endless cosmic ocean. Still others say this might all be just one breath of a cyclic universe, and our current universe is the rebirth after a previous universe's collapse. We don't know which is correct, or even whether these theories approach the truth. But we know one thing: we still stand at the boundary line, which is the beginning of time and the end of our understanding. In the early 1970s, a physicist gave us an answer that seemed crazy yet elegant. The universe might not have cost any energy at all. His name was Edward Tryon. His claim was shocking. The universe wasn't born from some existence, but fluctuated out of thin air from a peculiar quantum nothing. You might ask, how could nothing create a universe teeming with galaxies and vast energy? This is exactly what makes quantum mechanics amazing. In classical physics, nothing is nothing, empty, silent, vacuum. But in the quantum world, nothing is actually a boiling ocean. Everything is unstable. Particles and antiparticles, space and time, can all probabilistically appear at any moment and then disappear. This is called quantum fluctuation. But don't misunderstand, this fluctuation isn't random. It's strictly constrained by quantum rules. In this ambiguous zone, even time and space become indefinable. Could our universe be just one such fluctuation? A flash that accidentally became eternal? This seems impossible. Our universe has so much energy: light energy, heat energy, kinetic energy, energy in mass. But this is exactly where Tryon's brilliance lies. He said we missed a key factor: gravitational potential energy. In the universe, gravitational potential energy is a special form of energy. It doesn't emit heat and light like photons, nor is it obviously visible like motion, but it's almost everywhere. And it's negative. To make two celestial bodies move apart, you must work against gravity, inputting energy. When bringing them closer, energy is actually released. This is gravity's negative potential energy. Tryon's logic was this: positive energy plus negative energy equals zero. Light, heat, and matter are positive energy. Gravitational potential energy is negative energy. The universe's total energy ledger, adding and subtracting, comes out to exactly zero. What does this mean? It means our universe, from the perspective of energy conservation, cost absolutely nothing. It could be a natural fluctuation under quantum rules, violating no physical laws, and could exist forever. But philosophers aren't satisfied with this. They say physicists have only pushed the origin problem from one point to another fuzzy point. You say the universe comes from quantum fluctuations, but I ask, where do the fluctuations come from? You say it's a quantum nothing, but I ask, what is that nothing? Faced with these questions, physicists often smile slightly and continue forward. They're more concerned with whether the next theory can produce results, not philosophical ultimate explanations. The famous physicist Stephen Hawking also stood on this side. He proposed that our universe was born at a point where time and space no longer had meaning. There, only quantum probability and uncertainty governed everything. No before, only emergence. And this emergence might not be an isolated event. Perhaps such fluctuations occur more than once, and our universe is just one small bubble in an infinite ocean of bubbles. We call this the multiverse. Our universe was born from fire, an unbearable starting point, the hot, brilliant, surging Big Bang. But what will its end be? Will it burn again or gradually freeze? This question has puzzled generations of cosmologists. Once, we couldn't determine whether the universe would expand forever or eventually turn back. For a time, many believed that gravity would eventually halt the universe's escape, slowly stopping its expansion and then reversing back to itself. That would be a spectacular collapse. Galaxies falling back, stars disintegrating, temperature rising, the universe contracting from outside in, heat waves reborn. Initially gentle heating, but as collapse approaches its end, everything would accelerate. Temperature breaking through millions, billions, trillions of degrees, all matter compressed into pure energy, space curved, time disordered. At that moment, quantum forces and gravity would engage in their final game. Perhaps right at that edge, the universe wouldn't end but would bounce back. From extreme density and temperature, a new Big Bang would erupt. No longer an end, but rebirth. Stars would once again illuminate the darkness. Atoms would recombine. Life would be born again. Perhaps even we would exist again. This is the cyclic universe theory. Big Bang, expansion, contraction, great fire consumes all, then it happens again. If this is true, then the universe we're in right now is just one chapter in an endless cycle, a grain of sand, a wave, a breath. Of course, all this remains to be verified, because current observations tell us the universe has no intention of collapsing. Instead, it's accelerating its expansion, galaxies moving away from each other, space becoming colder and more sparse, until stars extinguish, black holes evaporate, and everything sinks into eternal silence and darkness. This is heat death, not an end in flames, but a gradually cooling death. No explosion, no cataclysm, only a long, irreversible freeze. Fire or ice, burning out or freezing to death, or cycles repeating. This is the question of the universe's fate, and also our inquiry into ultimate meaning. Some will question cosmologists. You've just changed the wording, circling around the problem. If the universe cycles endlessly, where did the first universe come from? If the universe will reach heat death, why did it begin? If everything is destined to fade away, what meaning does our existence have? But cosmologists often just smile lightly, pointing to infinite past and infinite future. In that inexhaustible ocean of time, perhaps some questions don't need answers. Perhaps it's precisely because of the unknown that the universe is worth gazing upon. We once thought the universe's future was sealed. Expansion would never stop until everything extinguished, falling into cold and void. This is the ice ending. But not all cosmologists accept this cold picture. In 2001, Paul Steinhardt proposed another cosmic fate, a universe without end. He called it the ekpyrotic universe. This word comes from Greek, meaning fire that consumes everything. In this model, the universe isn't isolated, but a thin sheet of space floating in higher dimensions. Our universe is just one brain, with a corresponding universe opposite to it. They're like two stretched drumheads, quietly approaching each other in higher dimensional space. When they collide violently, a creation event occurs, a new Big Bang. This isn't a one-time origin, but a cyclic cosmic reincarnation. Two brains slowly approach, collide, expand, age, approach again, cycling endlessly. Every death of a universe nurtures the birth of another. Someone might ask, if each universe experiences entropy increase, wouldn't this cycle become increasingly chaotic? Steinhardt's answer is no, because when the two brains expand extremely and separate, all entropy increase is stretched thin and dispersed, as if diluted to invisibility. The new universe is pure, bearing no ancestral trauma. Of course, most cosmologists don't accept this neat picture. They question whether this entropy reset is just theoretical fantasy. And more importantly, even if this cycle really exists, who caused the first collision? Where did the first pair of brains come from? This still doesn't answer the deepest question, the universe's ultimate origin. So our perspective is magnified again. Perhaps our universe is just part of a much larger structure, the multiverse. Perhaps in this invisible ocean of universes, our universe is just a drop of water, a bubble, an accidental ripple. If this is true, the ultimate origin isn't in our universe, but in this deeper ocean. You see, we seem to be going further and further. The more we ask where things come from, the closer we get to the unknowable. But this is exactly what makes cosmology so fascinating. Every answer is the entrance to a bigger question. Like collisions between brains, every thought ignites a new explosion. Robert Dicke was one of the most insightful physicists of the 20th century. His most famous contribution might be when he received the call from Penzias and Wilson, realizing the enormous significance of their discovery of cosmic microwave background radiation. And it was precisely through this discovery that many unsolved mysteries of cosmology began to see the light. But Dicke's thinking wasn't limited to this. He deeply studied the universe's fundamental properties, especially inspired by Paul Dirac's peculiar insight. Dirac noticed that certain physical constants in the universe had a mysterious connection with the universe's age. His discovery was shocking. He combined some fundamental physical constants and arrived at a value that matched our universe's age. This wasn't just a numerical coincidence, but seemed to reveal an intrinsic connection between the universe and its evolutionary process. At first glance, this discovery might seem like just a surprising coincidence. After all, physical constants are usually stable, while the universe's age continuously changes with time. But for Dicke, this coincidence hid deeper meaning. These numerical coincidences might be conveying some profound truth about the universe, a connection beyond the ordinary. It might be quietly shaking our understanding of the universe's foundation. In our understanding of the universe, there's a profound and revolutionary belief called the Copernican principle. This principle's core idea is, we are not special. We don't reside at the universe's center. We're just ordinary life on an ordinary planet beside an ordinary star, in an unremarkable corner of the Milky Way, an insignificant existence in the vast universe. This concept's origin can be traced back to Galileo removing Earth from the universe's sacred center, and later astronomical observations telling us that the Sun is just one of hundreds of billions of stars in the Milky Way, and the Milky Way is just one of billions of galaxies in the universe. The Copernican principle's philosophical power lies in encouraging us to abandon the illusion of anthropocentrism, believing we have no special position in the universe. It was based on this non-special premise that Einstein and other scientists were able to mathematically construct models of the universe. To this day, this principle remains the cornerstone of modern cosmology. But Dicke saw the contradiction within it. He was inspired by Dirac's marvelous discovery. Dirac pointed out that when some fundamental physical constants of the universe are combined, they surprisingly yield a result matching the universe's current age. This seemed like an inexplicable numerical coincidence, because physical constants are fixed while the universe's age is constantly growing. Many thought this was just coincidence, but Dicke didn't think so. He realized this wasn't coincidence, but a selection effect. We cannot exist at any random moment in the universe. For example, when the universe was very young, stars hadn't formed yet, so the heavy elements we need, like carbon, oxygen, and iron, hadn't been synthesized. And these elements are the foundation upon which life depends. Dicke pointed out that only at just the right stage of the universe, when stars had evolved through enough generations to scatter heavy elements throughout the universe, could life possibly be born. In other words, we see this just right universe because only in such a universe can we exist. This shook the core assumption of the Copernican principle. We're indeed not at the universe's spatial center, but we must be in a specific time window, a moment suitable for life's existence. And this moment is by no means random. Therefore, Dicke proposed a new concept to supplement the Copernican principle: the anthropic principle. The anthropic principle tells us that our position in the universe is neither random nor ordinary. We appear at this time, this place, near a stable star, dwelling on a carbon-rich planet, not because the universe is like this everywhere, but because only such a position allows our existence. In other words, the places in the universe where we can exist are themselves extremely special. Some physicists have even pushed this thought to deeper levels. They noticed that the universe can support life not only because of carbon or stars, but because the fundamental constants that support the entire physical world's operation are just right. For example, if the electron's mass were hundreds of times larger than now, if gravity were a bit weaker or electromagnetic force a bit stronger, if nuclear forces couldn't stabilize atomic nuclei, or if dark energy were too powerful preventing galaxy formation, then this universe might not even have the most basic atomic structures, let alone stars, planets, life, and humans. But the problem is, these values that determine the universe's fate have no known physical theory to explain why they are this way and not other values. They seem precisely tuned, sitting right in an extremely narrow window suitable for life. This leads to a famous problem in cosmology, the universe's fine-tuning problem. People are divided into two attitudes about this. One view holds that this is just a tautology. You can, of course, only find yourself in a universe that can support your existence. Otherwise, you wouldn't be here asking this question. It's like how fish don't question why water is always so wet. Because without water, they wouldn't exist. The other view questions, are we really willing to accept this explanation? Just because we're here, shouldn't we ask why this allows us to exist? They believe this is just how it is, isn't a satisfying answer. Are we living in an accidental universe? Or does the universe itself have some deep mechanism that designed or selected rules allowing life to exist? If the anthropic principle is true, if we exist because we were selected from among many possible universes, does that mean these universes aren't products of imagination but really exist? If the answer is yes, then the next question emerges. How many of these universes are there? 1, 10, billions, or infinitely many? Thus, a bolder hypothesis emerges. The universe we're in might just be a drop in the ocean of universes. The anthropic principle no longer just tells us why we're here. It might suggest there are other places, perhaps other versions of us. This hypothesis is the multiverse. At the end of the 20th century, the physics community harbored a grand dream: to find an ultimate theory that could unify all forces of nature, a theory of everything. This dream drew almost all eyes toward the same direction: string theory. This was a revolutionary viewpoint. All seemingly different fundamental particles in the world are actually tiny invisible strings, vibrating in different ways. Electrons, photons, quarks aren't different things, but different notes of the same thing. This isn't science making music. It's almost like the universe composing poetry. Everything comes down to one most fundamental resonance. Physicists once believed that once we mastered the laws of string vibration, we could unlock all secrets of the universe, unifying everything from quantum mechanics to general relativity. This vision was so beautiful and alluring that it was even called the ultimate symphony of the universe. However, the beautiful dream began to shatter upon entering the 21st century. String theory's mathematics became almost insanely complex, and it didn't provide a unique model of the universe, but instead gave a vast number of possible universes. This despairing surprise has a name: the string theory landscape. It tells us that string theory doesn't point to one unique universe, but to 10 to the power of 500 possible universes. Among these universes, each has different physical constants, numbers of dimensions, and fundamental force strengths, and the vast majority are dead, cold worlds unsuitable for life. This completely overturned people's initial expectations. We had hoped that string theory would naturally select our universe, like revealing an answer, standing out from all possibilities. But now, string theory seems to be saying, the universe you're in is just a random sample. We weren't chosen, we just happen to be born in a place that allows our existence. This leads to a philosophical conclusion. Perhaps we don't live in the only reality, but among countless possibilities, we happen to appear in a just right version. String theory didn't end the quest for a theory of everything. It pushed us toward a deeper maze, a mathematical landscape composed of countless possible universes. Our specialness might just be an accident. Scientists believe that in the extremely brief moment after the universe's birth, an incredible expansion occurred, which we call inflation. In just 10 to the power of -36 to 10 to the power of -32 seconds, the universe expanded by 10 to the power of 40 times in the blink of an eye. This explosive expansion explains why the sky is so uniform and smoothed out the early universe's wrinkles. However, we still don't know what triggered inflation or what made it suddenly stop. This mystery opened up a more stunning conjecture. Perhaps it never stopped at all. Thus, a radical concept was born: eternal inflation. In this theory, inflation isn't a relic of the past, but an eternally ongoing state. The universe is like a pot of boiling liquid, constantly producing bubble universes in an endless expanding ocean. Each bubble is the birth of a new universe, and we are life within such a bubble. When inflation freezes in a certain region, the inflation energy transforms into matter and radiation, thunderously injecting into a brand new universe, becoming the origin of everything in that realm. But the key is that each bubble universe might have different physical laws. Some universes have extremely strong gravity, some can't form atoms at all, and most are dead, cold wastelands unable to accommodate life. And we happen to be born in a just right universe. In this cosmic lottery of physical constants, we hit the jackpot. This might explain the so-called mystery of cosmic fine-tuning. But here's the problem. If these bubble universes are isolated from each other, and light cannot cross the expanding ocean between them, how can we prove their existence? If we can never see these other universes, are they still part of science? Or are they merely metaphysical fantasies dressed in mathematical clothing? In the early 1990s, physicist Lee Smolin proposed a radical and fascinating idea: universes might undergo natural selection. He imagined, if there were some mechanism that could select universes suitable for nurturing life, what would it look like? He turned his attention to the most extreme and mysterious objects in the universe: black holes. Black holes are the remnants of dead stars. After a supernova explosion, massive stars collapse into an infinitely dense singularity, where space and time curve to extremes. Under these extreme conditions, Smolin proposed that perhaps black holes are not endpoints but starting points. Perhaps within each black hole's depths, an entirely new universe is born. This is not fantasy. We observe about 5,000 stars exploding as supernovas every day, each potentially forming a black hole when it dies. Each black hole could potentially become the cradle of a new universe. In other words, our universe might be nurturing millions of baby universes every day. But these new universes aren't perfect copies of their parent. Their physical constants might be slightly different. Just as children on Earth don't perfectly replicate their parents, these baby universes have their own genetic codes. If they can also produce stars and black holes, they can continue to reproduce, having their own descendant universes. Conversely, if a universe's physical laws cannot nurture stars or form black holes, it's like an evolutionary failure, childless and doomed to extinction. Thus, in this cosmic scale competition, those universes that can reproduce offspring, universes that can produce black holes, gradually dominated the universe population. This is exactly what Smolin proposed as cosmic natural selection. Just as life needs suitable genes and environment, universes also need suitable physical laws to continue. Black holes are the universe's reproductive system, and the universe's laws are its genetic code. But how did life quietly make its entrance? Remember, any universe that can form stars will also forge carbon, oxygen, iron, sulfur, and other chemical elements within stellar cores. These are the essential ingredients for life. Therefore, universes that can form black holes often also possess the soil to nurture life. Perhaps our existence is not merely accidental, but the result of generations of cosmic selection. Although cosmic natural selection is a creative and fascinating idea, it still cannot avoid a more fundamental question. Where did the first universe come from? If our universe is just the offspring of some parent universe, then whose mother was that parent universe? Before it, how many universes were evolutionary dead ends? This hypothesis is like a cosmic genealogy game, where each generation of universes nurtures the next, but we ultimately ask, how did the first generation begin? This is like trying to explain the evolution of life while skipping the origin of the first cell. Therefore, although cosmic natural selection provides an elegant self-consistent mechanism, it also makes the entire cosmic picture more complex. We understand why certain universes can survive, but we still don't understand how the first universe was selected into this system. This model addresses the problem of adaptation but doesn't touch the mystery of origins. Logically speaking, natural selection is a screening mechanism, not an origin mechanism. It tells us which universes will reproduce and survive, but cannot tell us why there's a universe system for it to select from. Thus, the ultimate question still echoes at the end of thought. At the beginning of all things, How did that first universe emerge from nothing? Perhaps the universe wasn't selected, but was generated at some unreachable source. We're rapidly approaching the end of this cosmic story, but the questions raised still far outnumber the answers. How our universe originated remains as mysterious as it was 100 years ago. Multiple universes, quantum nothingness, eternal inflation. These ideas interweave like galaxies, but truth remains distant. The quest for a theory of everything continues, with physicists delving deeper into theories and new ideas constantly emerging. We don't know if or when we can truly solve this puzzle where mathematics and reality intertwine. But if we succeed, the secrets hidden in the universe's depths will no longer be mere riddles. When we debate whether nothing can give birth to something, when we search for exits in the multiverse's maze, perhaps we've already strayed from some deeper truth. The universe's charm lies precisely in its inexhaustibility. Just as stars burn not to reach an endpoint, but to illuminate every inch of collapsing and expanding time. Human contemplation is not meant to conquer mysteries, but to become eternally open vessels in our questioning. Embracing starlight and the unknown, embracing reason's sharp edge and philosophy's mist. Perhaps one day, when our civilization crosses hundreds of billions of light years, when mathematics' key finally touches the glimmer behind the Planck wall, we'll suddenly understand that the universe's ultimate answer was never some cold formula, but the fire of curiosity that has never been extinguished in countless eyes gazing at the stars across millions of years. I am watching, I am thinking, I am becoming the universe's way of understanding itself. If time is an illusion, then what are we experiencing? We've always thought time moves steadily forward, serving as the universe's backdrop. But what if time isn't an objectively existing dimension at all, but rather an experience fabricated by our consciousness? This seemingly science-fictional idea is gradually gaining support from more and more scientific research. From Einstein's relativity to quantum mechanics' strange phenomena, to modern neuroscience's research on the brain's time perception mechanisms, explorations across many fields gradually make us realize that time might not exist as we've always perceived it. It might be a flowing structure created by the dynamic relationships between matter, energy, and information. In other words, the so-called present, past, and future might just be our brain's way of interpreting the world. Our perception of time is merely a projection of deeper reality at the consciousness level. This understanding not only overturns traditional cosmology, but also provokes deep reflection. Is every moment we experience truly real, or an illusion woven by consciousness? Tracing along the threads of human civilization, contemplation of time has spanned thousands of years. From ancient sages' philosophical wisdom to modern scholars' scientific discussions, countless viewpoints about what is time have continuously collided and evolved in this river of thought, quietly reshaping our understanding of this mysterious dimension. In ancient civilizations, time wasn't merely the sequence of sunrise and sunset, but was viewed as a key force of cosmic order and universal change. For example, the ancient Greek philosopher Heraclitus left a profoundly influential saying, "Everything flows." He believed that the only unchanging thing in the world is that everything changes. In his view, time is change itself. He even used fire to symbolize life's continuous transformation, flames burning ceaselessly like the world's never-ending flow. As philosophical thought developed, unlike Heraclitus' views on time and change, later philosophical schools like the Parmenidean school began exploring whether time could be static. From eternal immutability to constant change, these collisions and contrasts are exactly what makes the philosophy of time fascinating. Plato advanced human thinking about time to a deeper philosophical dimension. He proposed a tension-filled worldview. Reality is divided into two levels, one being the constantly changing, uncertain sensory world before us, the other being the timeless, eternally unchanging world of ideas. In his dialogue, Timaeus, Plato painted such a cosmic picture. The entire world strives to imitate the perfect realm of ideas. The universe we inhabit is shaped by some divine order. It's not chaotic disorder, but attempts to approach some eternal perfection. Based on this, in Plato's view, time is the product of this imitation. He called time the moving image of eternity. This expression sounds obscure at first, but contains profound meaning. In Plato's understanding, eternity is static and perfect, while time is eternity's dynamic projection in the changing world. Time is like a flowing mirror, presenting constantly changing, imperfect reality, but its source and destination always point to eternity. So in Plato's philosophy, time is contradictory. It's both real, we can perceive and measure it, but also illusory because it's merely a projection of that higher reality. Entering the Middle Ages, philosophical thinking about time underwent a major shift. Religious faith began to deeply intervene in time's definition. At that time, time was no longer just nature's rhythm or philosophy's abstract concept, but a sacred clock carrying divine will. Many thinkers, based on Aristotle's theories, similarly viewed time as a continuously changing system, but they gave time higher meaning, believing time was created by God, starting from some sacred origin and moving straight toward the world's end. This timeline isn't chaotic disorder, but has a clear purpose, pointing toward ultimate salvation. The most representative figure was Saint Augustine. In his Confessions, he left a passage that still provokes deep thought. The past no longer exists, the future hasn't arrived yet, so what exactly is time? He believed that time isn't an objective existence as we usually think, but is deeply embedded in human consciousness. The reason we can perceive time's passage is because memory carries the past, attention focuses on the present, and expectation points to the future. This unique understanding closely connects time's essence with human consciousness activities. For Augustine, time is both the cosmic rhythm set by God and a unique experience existing in the human soul. He placed time in a delicate position between humans and God, making it possess both sacred and human characteristics. Meanwhile, the Renaissance wave sparked a profound intellectual liberation. During this period, classical wisdom was reawakened, scientific spirit began to sprout, and people began boldly challenging old concepts of time. Thinkers like Giordano Bruno and Nicholas of Cusa proposed an idea that was almost heretical at the time. The universe isn't finite, closed, and static, but infinite and constantly changing. Bruno believed the world has no boundaries, the universe has no center, and time is no longer a linear progression scale, but like an endless spatial dimension where all things freely generate and continuously evolve. The world he imagined was a dynamic whole woven from countless events, quietly rewriting the entire situation at every moment. In that era, such views were dangerous. His ideas not only overturned the orderly mechanical universe depicted by medieval theology, but directly challenged religious explanations of world structure. Bruno paid the price with his life, but undeniably, these radical explorations laid the groundwork for the later scientific revolution. Humans began to realize that time and space might be far more complex, free, and fascinating than we habitually understand. With the arrival of the scientific revolution, human understanding of time underwent a complete transformation. In the early modern period, Newton emerged prominently. In his Mathematical Principles of Natural Philosophy, he proposed an unprecedented concept: absolute time. In his view, time is independent of external world changes, like an invisible cosmic clock, flowing steadily and uniformly, building an unchanging background stage for the entire universe. For Newton, time is like a stage, celestial bodies are actors, mechanics is the script, and everything unfolds orderly on this absolute time axis. This view laid the foundation of classical physics and successfully explained numerous phenomena like planetary motion and object movement. But with the progress of empirical science, some discordant phenomena quietly emerged. For instance, why is the speed of light absolutely constant in any reference frame? Why do certain planetary orbits subtly deviate from Newtonian mechanics predictions? These questions gradually shook Newton's theoretical edifice of eternally unchanging time. It was in such confusion and exploration that these questions, like tiny cracks that couldn't be ignored, finally triggered an intellectual earthquake: the birth of Einstein's relativity. He proposed that time isn't absolute. It bends with speed and gravity. Thus, humanity moved from the classical belief that time is the universe's pointer to a more complex and mysterious space-time world. Once, time was treated as the universe's backdrop, eternally fixed and immutable. However, this understanding was completely overturned in the 20th century. scientists gradually discovered that time doesn't exist independently. It's closely interwoven with space, forming a unified structure, space-time. This viewpoint's emergence meant that time was no longer that isolated, eternally ticking clock, but a variable existence. It slows down due to speed and bends in strong gravitational fields. This breakthrough discovery completely shook time's status as a universal constant. Over several centuries, physicists' understanding of time underwent profound transformation. Under classical physics framework, time was viewed as an absolute observer. Newton defined time as absolute, real, and mathematically flowing existence. Whether objects move or not, regardless of how the universe changes, it ticks forward at a uniform, unchanging rhythm, as if there's an invisible cosmic clock silently recording everything. Under this framework, time is like an unwavering stage where all events in the physical world, planetary motion, apple falling, clock ticking, are dramas performed on this stage. It doesn't participate or interfere, merely existing as a constant presence. This understanding highly matches our daily experience. After all, every minute and hour in life seems as fixed as numbers on a clock, neither biased nor hurried. However, it was precisely this seemingly natural view of time that was gradually broken, revealing time's other face. It might not be as stable and absolute as we thought. Entering the 20th century, an epoch-making intellectual revolution completely rewrote our understanding of time. Before special relativity was proposed, under Newton's classical mechanics system, time was considered absolute and uniformly flowing, unrelated to objects' motion states in space. Albert Einstein's special relativity first shattered the myth of time's absolute invariance. He pointed out that space and time are actually unified, interwoven together, forming a four-dimensional structure called space-time. In this new framework, time is no longer the universe's backdrop, but a dimension that can be changed and stretched. An astonishing discovery followed. Time is relative. This means that when an object moves at near-light speed, the time it experiences slows down. This isn't just mathematical deduction. It's been verified by multiple experiments. For example, in high-speed moving particles, scientists indeed observed them living longer. On flying aircraft or satellites, atomic clocks run tens of millionths of a second slower than ground-based atomic clocks. Despite the tiny difference, it has enormous scientific significance. Einstein's general relativity further expanded this thinking. He told us that gravity also slows down time. Massive celestial bodies like Earth and the Sun bend surrounding space-time, and this bending not only drives objects' gravitational motion but also makes time flow slower in strong gravitational regions. This isn't fantasy, but verified scientific reality. Take our daily used GPS navigation system as an example. These time differences must be considered, or maps would have errors of hundreds of meters. So, from classical mechanics' uniformly flowing time to modern physics' revealed variable space-time fabric, humanity is redefining what is time. It's no longer an absolute background, but a dynamic structure in which matter and motion participate. This conceptual transformation completely overturned our intuition about time and brought us closer to the universe's true operational nature. Thermodynamics research revealed another wonderful aspect of time. In classical mechanics, object motion follows time-symmetric laws. Looking forward or backward, the formulas are the same. But thermodynamics tells us that time actually has direction. This direction is guided by entropy, the measure of a system's disorder level. Imagine gas molecules trapped in a box, initially perhaps orderly squeezed together, but as time passes, they spontaneously diffuse to fill the entire space. This isn't accidental, but the natural result of entropy increase. Systems always evolve toward more chaotic, disordered states. It's precisely this irreversible progression from order to chaos that gives time a distinct arrow, allowing us to distinguish past from future. In the microscopic world, individual particle motion follows time-symmetric rules. However, when many particles gather, statistical effects begin to dominate, and the overall system inevitably evolves toward higher entropy. Thus, the arrow of time is no longer time's inherent property, but the statistical result of collective behavior of many particles. Moreover, the thermodynamic arrow of time is deeply connected to information generation and loss. Whenever a system becomes more disordered, information about its past state remains in the entropy increase process, forming a kind of memory, while the future is full of infinite possibilities, maintaining an open state. So when we say time is flowing, it's actually energy changing, information dissipating, and systems continuously moving toward more disordered directions. It's precisely this duet of thermodynamics and information theory that adds both real and profound dimensions to our understanding of time's nature. In cutting-edge theoretical physics, time is no longer stage lighting with its own engine, but more like an emergent phenomenon of collective cooperation. Scientists discovered that when we zoom in to the extremely small Planck scale, the continuous picture of space and time collapses, replaced by a discrete world assembled from countless quantum building blocks. In the two research lines of loop quantum gravity and causal dynamical triangulation, time and space aren't preset coordinates, but emerge when these quantum building blocks collide and exchange information. You can imagine it as only when every string in a symphony vibrates simultaneously does music flow in our ears. A single string doesn't produce time's melody. This viewpoint is similar to quantum mechanics' idea that measurement creates reality. In the Wheeler-DeWitt equation, the time variable disappears, and only when we observe does a time point get reconstructed in the moment of wave function collapse. In other words, time might just be a parameter we use to organize the sequence of events when describing cosmic evolution, not the most fundamental thing. When we question, is time really an eternal, continuous flow? Or is it like temperature and humidity, merely a manifestation of macroscopic phenomena? Once we accept this perspective, time is no longer mysterious, but like a detailed map drawn from massive data and microscopic correlations. It's hidden in the flow of information and energy, slowly emerging with the universe's evolution. Because of this, one of the core tasks of today's theoretical physics and astronomy is to build a framework that can unify quantum mechanics and relativity, making time both relative and able to grow from more fundamental mechanisms. Isaac Newton, in Mathematical Principles of Natural Philosophy, portrayed time as a never-resting guardian who moves forward at the same rhythm regardless of what happens. He completely separated time from the material world, calling it a true mathematical entity, the foundation of cosmic operation. In this framework, time became the only constant stage in nature that couldn't be disturbed. Whether you're on Earth or in a spaceship, whether you're running fast or standing still, everyone's clock ticks at the same speed. It was precisely because of this absolute time that scientists could precisely write equations of motion, calculate planetary orbits, predict collision results, and even drive the entire glorious era of classical physics. This viewpoint seems natural. The clocks we see daily, from kitchen timers to car dashboards, tick reliably, never changing speed because we run fast or stand far away. But when new observations and experiments appeared, scientists found that some phenomena simply couldn't be explained by this smoothly flowing time. Thus, a great discussion about time's nature began. In 1905, Einstein completely overturned Newton's absolute time concept with a single paper. He told us that time isn't constant like an unchanging pendulum, but is closely connected to speed. When you fly at near light speed, your time slows down. Imagine two identical precision clocks, one staying on Earth, one boarding a high-speed spaceship. The spaceship's clock runs slower than Earth's. This isn't science fiction, but fact verified multiple times by laboratory and particle accelerator experiments. Subsequently, Einstein took another step in general relativity. Gravity can also distort time. Around black holes, space-time is compressed and distorted beyond measure, and clocks near black holes tick slower. Even satellites in Earth's orbit, though not as fast as spaceships, also have slightly slowed time due to Earth's gravity. If these effects aren't accounted for, GPS navigation would have errors of hundreds of meters. Thus, time transformed from backdrop to interactive actor. It mixes with space into a four-dimensional stage, stretching due to high-speed motion and bending due to gravitational pull. This not only made physicists reconsider time, but also made philosophers rethink. From the block universe theory perspective, if time can stretch, can our boundaries between past, present, and future still be as definite as before? Block universe theory even proposes that every moment in the universe is like a frame, eternally coexisting, and our so-called flow might just be consciousness switching between these frames. When technology can't function without relativistic corrections, the real world repeatedly proves that time isn't unchanging, but a dynamic existence interacting with space, speed, and gravity. From then on, our understanding of time would never be as simple as before. How miraculous is the speed of light? Precisely because it's the same speed for everyone, regardless of the observer's own speed, the measured speed of light remains constant. To ensure light speed constancy, time and space undergo corresponding changes. Time stretches, length contracts. Moreover, simultaneity isn't as simple as we imagine. Take two lightning strikes hitting both ends of a moving train as an example. A person standing on the platform might think they occur simultaneously. But when you're speeding on the train, you'll see the front lightning first, because light needs a shorter distance to catch up to you. These phenomena fully demonstrate that whether two events occur simultaneously depends on the observer's motion speed. All this reveals an astonishing truth. Time isn't a unified metronome. It changes with speed. Only because in daily life our speeds are far below light speed are these strange effects hard to perceive. When speed approaches light speed, time really slows down. When gravity is extremely strong, such as near black holes, time is compressed to extraordinary slowness. Space and time are no longer two independent dimensions. They merge into one, weaving the four-dimensional stage we call space-time. In this picture, events no longer just occur at some time point, but exist within the entire space-time grid. Traditionally, we view now as an absolute moment, but relativity tells us that different observers view now in different ways. This is not just physics domain, but a challenge to our intuitive feelings. When simultaneity becomes relative and time can stretch, are our past, present, and future still as distinct as before? Perhaps time's flow is more a cognitive creation of our brain processing world information. These discoveries not only revolutionized physics, but also shook philosophical foundations. Our experience of past, present, and future might just be mental projections under the interweaving of speed, gravity, and information. When science enters the microscopic world and universe's edge, time's essence truly surfaces. Imagine, if we weren't on Earth but in other corners of the solar system, what would time be like? Planetary rotation and orbital rhythms determine their unique temporal pulsations, profoundly affecting how life there perceives day-night and seasonal cycles. First, look at Mars, the natural sprinter. It takes only about 24.6 hours to rotate on its axis, similar to Earth's 24 hours, but those extra 6 minutes mean dawn and dusk on Mars are slightly longer. If you settled on Mars, daily routines, crop growth, and even biological clocks would need adjustment for this tiny difference. Now look at Venus, the slow-motion master. It not only rotates backward but extremely slowly, taking 243 Earth days to complete one rotation. In other words, Venus's one-day night cycle is longer than its orbital year, about 225 Earth days. This means one day on Venus is longer than 1 year. Imagine the wonderful experience of spending half a year in the same dawn. Or when night finally falls, people have just completed one complete life cycle. Completely different from Venus are Jupiter and Saturn, called eternal travelers, whose timescales are even more astonishing. A year is truly astronomical. Jupiter takes about 12 Earth years to orbit the Sun. Saturn takes nearly 30 years. Their seasons, climate, and even storms brew slowly during these long journeys. If there were life there, it might have long adapted to this slow life rhythm. Theoretically, the gravitational strength differences of these gas giants might make clocks in their atmospheres run at different speeds. Atmospheric layers near deep gravitational wells would have slightly slowed time, while observing storms racing in high atmospheres would theoretically present another temporal rhythm. Back on Earth, our 24 hours and 365.25 days form stable seasons and biological rhythms. But on other planets, with vastly different day-night cycles and seasonal lengths, social customs, work-rest patterns, and holiday celebrations would all be rearranged following planetary astronomical rhythms. Imagine a lifetime that takes decades to cycle, or in some planets' extreme environments, situations changing dramatically within seconds, like crossing countless storms. This is the shock that planetary time brings to explorers. Of course, don't forget Einstein's reminder. Each planet's gravity also fine-tunes time. Where gravity is stronger, clocks run slower. Theoretically, on a planet with certain mass like Venus, due to slight differences in gravitational field strength between deep valley bottoms and mountaintops, according to general relativity, time flows slightly slower at valley bottoms than at peaks. But this difference is extremely difficult for humans to intuitively perceive in practice. If we compare the entire universe to a movie, then the main thread of time truly began only at the moment of the Big Bang. According to modern cosmological theory, about 13.8 billion years ago, everything was squeezed together with unimaginably high density and temperature. At that moment, even before and after couldn't be distinguished. Under general relativity's framework, time and space are an inseparable whole spacetime. The spatial expansion triggered by the Big Bang is essentially spacetime expansion. Time, as one dimension of spacetime, naturally began in this process, evolving together with space. Today, from the old photograph of cosmic microwave background radiation, we dimly glimpse the blurred picture of the universe's early birth. Spacetime was still like a wrinkled cloth, becoming smooth and orderly as temperature dropped and expansion unfolded, allowing events to occur one after another. In the extremely short time after the Big Bang, cosmic space expanded rapidly at exponential speed like hitting fast forward. This unprecedented race not only stretched originally tiny quantum fluctuations to astronomical scales, but also laid the foundation for later galaxies and galaxy clusters. Even more amazingly, inflation not only stretched space but made the universe more uniform and flat on large scales, creating conditions for subsequent structure formation. You must know that without this super-instantaneous change, tiny quantum fluctuations might never have developed into the magnificent galaxies we see today. Matter distribution and structure formation in the universe would be greatly affected, making it difficult to form the ordered structures we see today. It was precisely because of that extreme stretching that the universe gained its framework of order. The cosmic microwave background is like an echo from the early universe, opening a window to 13.8 billion years ago. It's the afterglow left by the Big Bang, expanding with spacetime and stretched to today's detectable microwave band. Through satellites, we observed tiny temperature fluctuations across the sky. These are fingerprints of primordial quantum fluctuations, infinitely amplified during inflation. These modeled hot and cold patterns not only verify the inflation model but tell us about the universe's initial density distribution, how matter began to cluster, brewing galaxies, galaxy clusters, and even our Milky Way. More interestingly, the temperature across the entire sky is almost uniform, meaning that around inflation, the universe achieved astonishing thermal equilibrium, making space and time undergo dramatic evolution under specific conditions. On this same enormous and relatively smooth cosmic canvas, these subtle inhomogeneities and density perturbations, under gravitational influence, gradually attracted more matter to slightly denser regions over time, forming seeds of large-scale structures like stars and galaxies. In other words, the cosmic microwave background not only tells us how uniform the universe is, but reveals why the universe became non-uniform. It's the most direct witness to time unfolding on large scales and structures beginning to grow. The universe isn't a simple arrangement of stars, but a grand grid woven from galaxy clusters and dark matter filaments, which we call the cosmic web. On this grand stage, gravity not only shapes matter distribution but subtly influences time's passage. According to Einstein's general relativity, the stronger the gravitational field, the greater the spacetime curvature, and the slower time flows. At nodes where galaxies are dense and dark matter highly concentrated, powerful gravity acts like an invisible time decelerator, making time flow significantly slower than in surrounding empty space regions. In gaps dominated by dark energy, where matter moves apart, gravitational fields are weaker, and time flows slightly faster. As galaxies slowly grow, collide, and merge in this grid, their gravitational history also changes. This not only leaves marks in cosmic structure evolution but creates subtle time differences in different regions. We can view the cosmic web as a vast clock system, where every galaxy cluster and dark matter filament has its unique temporal rhythm. More interestingly, as the universe continuously expands, This grid keeps stretching and reorganizing, and time measurements in various regions adjust accordingly. Time measurements change with spatial deformation. In other words, the cosmic web is not only matter's skeleton, but also a dynamic time machine, performing on macroscopic scales the magnificent dance of gravity and dark energy, the interweaving of time and space. Within this vast cosmic web grid, there exist regions called voids, like wastelands between galactic filaments. In these places, gravitational potential energy is extremely low, space-time curvature is weak, and time flows relatively faster. While at nodes where galactic filaments and galaxy clusters gather, powerful gravity slows down time. When you step into the universe's strangest theater, near black holes, time's rhythm is completely rearranged. There, gravity acts like an invisible giant net twisting spacetime, and the closer to the event horizon, the slower time flows. From a distant observation, it's like watching someone approach a black hole in slow motion, finally seeming to freeze in midair, never crossing that invisible threshold. But this isn't an instantaneous phenomenon. Depending on the black hole's mass, according to general relativity, the more massive the black hole, the deeper the gravitational well around it. You'll first experience a gradual deceleration process, getting closer to the center with time dilation effects continuously strengthening, the gap with external time flow growing larger, until at the event horizon, this effect reaches its extreme. Here, even light speed seems gentle, and any rapid traversal or high-energy jets obediently slow down before this space-time giant web. For distant observers, this seems like an eternal slow-motion epic. For the person falling into the black hole, due to their local inertial frame, they won't notice any abnormality in time's passage before crossing the event horizon, still feeling every second passes normally. But once past the event horizon, there's no return. This journey of temporal displacement not only fills us with curiosity about black holes' true nature, but makes us re-examine what time really is under the interweaving of extreme gravity and high-speed motion. Where does it slowly stop? And how does it reflect the universe's most hidden secrets? When we delve into the quantum world, time's nature presents even more mysterious characteristics. Inspired by quantum theory, some viewpoints suggest that time isn't a continuous smooth flow, but composed of discrete time quanta, like tick-tock basic units arranged in sequence. These independent moments connect with each other to form the time flow we perceive. Within quantum gravity theory frameworks like loop quantum gravity and string theory, researchers attempt to unify quantum mechanics with general relativity, proposing new hypotheses about time's nature, including the possibility of discretized time. These theories predict that at the Planck scale, time might exhibit discrete characteristics. However, since the Planck scale is far smaller than currently detectable laboratory ranges, verifying this hypothesis is extremely challenging. Fortunately, Earth provides a natural experimental field for verifying gravitational time dilation. Physicists successfully detected time dilation effects caused by gravitational differences by placing high-precision atomic clocks at different altitudes, even with height differences of just a few centimeters. Experiments show that clock rates vary with altitude, presenting tiny differences. This result directly verifies general relativity's prediction that the stronger the gravitational field, the slower time flows, confirming the physical reality of time dilation. Time's essence is far more profound than clock ticking. It's both an objective variable governed by physical laws and deeply interwoven with human subjective perception, thus not an unchanging absolute measure. Scientists discovered that the human body has a built-in precision biological timing system, internal biological clocks that regulate physiological rhythms like breathing and heartbeat. They help us coordinate daily life rhythms, but are easily affected by emotions and attention, causing deviations. Think about it. When you're fully absorbed in something, time seems accelerated, passing in the blink of an eye. But when bored or anxious, time seems infinitely stretched, with every second feeling extraordinarily long. Psychologists, through experiments having participants estimate durations of stimuli like sounds and light points, repeatedly verified a key conclusion. Time perception results from multiple factors including stimulus intensity, attention level, and emotional state. Sometimes, just a few seconds can be perceived by the brain as minutes of lengthy experience. Therefore, Time is no longer external uniform unidirectional flow, but personalized narrative generated from the interaction between inner world and sensory experience. Our subjective time perception is more like a variable speed mirror fluctuating with emotions than a clock's mechanical second hand. When we experience intense emotions like joy or fear, the brain enters a high arousal state, accelerating information processing and enhancing detail encoding, so time perception significantly lengthens, as if moving slower. Psychologists propose that this lengthening of time perception might be an adaptive mechanism. In crisis situations, slow-motion time perception can increase the effective duration for the brain to process critical information, improving survival response accuracy. When emotional state switches to low arousal mode, time perception shows opposite characteristics. For example, when engaging in monotonous repetitive tasks, the brain enters low energy mode, reducing sensitivity to time's passage, making even just a few minutes feel like lengthy cutscenes. This emotion-fluctuating time experience both gives us precise reaction ability in crises and makes daily time show elastic overflow or compression. The brain's constructed private clock is the core carrier of subjective time. This phenomenon reveals that time isn't purely objective linear existence, but cognitive construction formed when the brain processes information. From a philosophical perspective, philosopher Kant proposed in Critique of Pure Reason that time and space are innate forms of human sensible intuition, not objective containers independent of cognitive subjects. This means time's manifestation depends on human organization of sensory experience, not physical reality external to the mind. It should be clear that this philosophical perspective doesn't negate physics research on time's objective properties, but reveals the subjective mechanisms of time experience from a cognitive science dimension. Our emotions, memories, and expectations not only shape the texture of time experience, but profoundly influence our philosophical thinking about free will through cognitive construction. When we habitually view time as a stable river, we tend to think the future is a predetermined course, and our choices are merely passive products drifting downstream. But if we acknowledge that time is the mind's flowing thing, stretching and contracting with inner states, we question whether human decisions truly stem from free will or are constrained by temporal causal chains. As we wander through this millennial journey of temporal speculation, we finally discover that humanity's inquiry into time's essence is like a tacit dialogue with the universe. We're both deciphering spacetime's code and measuring consciousness's boundaries. From Plato's eternal image to Einstein's curved spacetime, from thermodynamic arrows' entropy-increasing fate to quantum worlds' discrete puzzles, time always reflects human cognition's limitations and breakthroughs through multiple facets. It's both a calculable physical variable in scientists' writings and a flowing metaphor in poets' hearts, and even more, the most intimate scale in everyone's life experience. When we pause for certain memories, heartbeat for certain moments, anticipate future possibilities, time condenses in consciousnesses folds into a lake uniquely human. Perhaps time's ultimate answer was never in clock's mechanical operation, but in the starlight flowing in our eyes when gazing at the sky, in the moment infant crying breaks silence, in memory's warm touch when looking back in twilight years. It's the rebel in an entropy-increasing universe, using emotion and thought's order to resist chaos's inevitability. It's finite life's gentle transgression against infinite eternity, making every moment an anchor of meaning transcending physical existence. When we finally stop obsessing over whether time is real and instead embrace this wonderful illusion woven by consciousness, perhaps we truly understand the eternal metaphor dancing in Heraclitus's fire basin. We are both time's observers and its most vivid creators. On this endless space-time journey, may we all engrave our own unique temporal verses in the universe's grand narrative through passionate existence. When the first Homo sapiens looked up, humanity's longing for the starry sky became irrepressible. Imagine 13.8 billion years ago, our universe was just a tiny point, unimaginably hot and dense to the point of bursting. But at that moment, bang, an unprecedented Big Bang exploded, and the universe was born. It expanded rapidly like a balloon while gradually cooling, slowly forming the world we know today, with matter, antimatter, and various radiation shuttling between. And now, the universe we can see with our eyes has actually reached a radius of 46 billion light-years. Wait, Isn't the universe only 13.8 billion years old? How can we see 46 billion light years away? This isn't just sounding far, it really is far. This is the distance that light has traveled through spacetime's expansion since the universe's birth, crossing 46 billion years of time to reach us. But note, this is only the limit of what we can currently see, the observable universe. Beyond this boundary where light cannot reach, what else is hidden? Are there more vast galaxies, mirror universes we can never reach, or completely different physical laws? Is the universe infinite, or is everything we understand today just a small tip of the cosmic iceberg above water? Next, we'll embark on a mind-blowing journey together, diving into the cutting edge of theoretical physics, exploring those ultimate puzzles that keep scientists awake at night, pursuing that question that has emerged in everyone's mind: what lies beyond the universe? But before we begin, we need to clarify one thing. What exactly do we mean by universe? When you look up at the starry sky at night, you might think you've seen the universe's entirety. But I must tell you, what you see doesn't even count as a tiny fragment of the universe. We're like beings at the center of a giant cosmic bubble, and the region within this bubble that we can see is called the observable universe. Come, let's dive into this bubble together and see how many unimaginable surprises this universe we thought we knew actually holds. Have you ever noticed that when we step outside, our field of vision is actually quite limited? At most, we can see a bit beyond the street across, and then our sight is blocked by the horizon. But beyond the horizon, things continue to extend. There are buildings, mountains, other people living completely different lives from yours. They're just temporarily out of your sight. Most interestingly, no matter where you are, when you look around from your position, you always feel like you're standing right at the center of the world. You clearly know this isn't true, but this feeling is deeply ingrained. This is a natural illusion brought by our eyes and position. The same illusion occurs when we observe the universe. From Earth, when we look up at the starry sky, we feel the universe is endlessly vast, seemingly extending infinitely, with us right at the center of this vastness. But in fact, the universe we see is just a fragment limited by speed. This limit is called the cosmic light horizon. Why can't we see farther? Because although light speed is the fastest in the universe, it's not infinite. The universe is too vast, too deep, too ancient. Light from many distant places is still on its way here. So what we call the visible universe is actually only the part whose light has had time to reach Earth. This light-illuminated region has a name: the observable universe. It sounds like advanced technology and powerful telescopes enable us to observe these places. But actually, it has nothing to do with instruments. It's a limit purely determined by physical laws, a visible boundary drawn by light speed and the universe's age. In other words, as long as light from some place hasn't reached us yet, we simply cannot know what's happening there. This introduces an important concept: the particle horizon. It defines the farthest boundary from which we can receive information. Once beyond this distance, no matter what happens in the universe, we can't see it or ever detect it. You think you understand the universe, but what you see is just the first screen of this cosmic panorama. Even more wonderfully, astrophysicists have further distinguished between the observable universe and the visible universe. The observable universe refers to all signals emitted after cosmic inflation ended, which we can theoretically receive. The visible universe is smaller, containing only signals that reached us from after the recombination epoch, when light began propagating freely. So different universe versions are like video previews of different qualities. What you can see depends on when the universe went online with its signals. Have you ever wondered, with the universe so vast, how far are the stars in the sky from us? They're not little light bulbs hanging from the ceiling, and we can't fly over with a measuring tape, so how do astronomers actually measure distances to these distant objects? Don't worry, scientists have a special set of cosmic measurement secrets. The first method you actually learned in high school, trigonometry. Don't underestimate this subject. It's a powerful tool for measuring the nearby universe. For example, planets in our solar system, or stars within dozens of light years in the Milky Way, can all be handled by this method. There's a key concept here called the parallax method. You can try it right now. Hold out a finger, close your right eye and look with your left eye, then close your left eye and look with your right. Doesn't the finger's position seem to shift? This is the parallax effect. As long as you know the distance between your two eyes and measure the finger's shift angle, you can calculate the finger's distance from you through triangular geometry. Don't you feel like a little cosmic distance measurer? But here's the problem: our eye's baseline is too short to measure distant stars. So what do? Don't worry, scientists figured this out long ago. We have a pair of super large eyes, Earth's orbit around the sun. You can imagine Earth orbits the sun once a year, so within 6 months, we can stand at two completely different positions. The first observation of a star is from one side of Earth's orbit. 6 months later, when Earth has moved to the other side of the orbit, we look again and find that this nearby star has shifted slightly in the sky relative to the more distant background stars. This tiny change is called annual parallax. With this shift angle and Earth's orbital diameter as baseline, we can use the classic Pythagorean theorem to precisely calculate how far this star is from us. Isn't that super clever? But you probably guessed that this method isn't omnipotent either. The farther the distance, the smaller the parallax, until it's almost unmeasurable. When trigonometry fails and stars are so far that even the smallest parallax is invisible, astronomers bring out another secret weapon, a type of rhythmically pulsating star called Cepheid variables. These stars aren't just ordinarily bright. They pulse rhythmically between bright and dim, like a giant heartbeat in the universe. As early as 1794, humans noticed these heartbeat stars. By the early 20th century, astronomers amazingly discovered an absolutely precise mathematical relationship between Cepheid variables' heartbeat periods and their true brightness. How to understand this? Simple. The slower a Cepheid variable pulses, the brighter it is. The faster it pulses, the dimmer it is. As long as you know its pulsing speed, you can determine how bright it actually is. It's like looking at candles in the distance at night. A bright one in your hand doesn't mean it's inherently brighter. It might just be closer to you. But if you know how bright each type of candle actually is, combined with how bright it appears now, you can deduce how far it is from you, right? Cepheid variables are exactly this type of standard candle in the universe. We just need to measure their pulsing rhythm and their apparent brightness to accurately calculate their distance from us. Even more amazingly, this Cepheid brightness scale can measure distances to galaxies 20 million light-years away. But wait, the story isn't over. 20 million light-years sounds far enough, right? But this distance is still just the tip of the iceberg on the scale of the entire universe. This time, what comes in handy isn't the twinkling heartbeat stars, but super explosions from the depths of the universe. Imagine, in some corner of the distant universe, in a binary star system orbiting each other, one aging star has degenerated into an extremely dense, compressed white dwarf, while its companion star is still burning and releasing energy. But nobody expected this white dwarf to become so greedy. It began frantically devouring its companion's matter, bit by bit, day by day, claiming the other's mass as its own, until one day, its mass exceeded 1.4 times that of the Sun. This is an uncrossable critical point in the universe. Boom! At that instant, this white dwarf completely lost control, undergoing a universe-scale explosion that released light even brighter than the combined total of all stars in a galaxy. This type of explosion is the famous type Ia supernova in astronomy. Amazingly, every type Ia supernova explosion has almost the same brightness. They're like standardized cosmic flashlights in the universe, making them another standard light source that helps us measure distant galaxies billions of light-years away. As long as we observe their brightness changes, we can deduce how far these explosions are from us, accurate and reliable across billions of light-years. See, we've gone from parallax methods dozens of light-years to Cepheid variables tens of millions of light-years, and now with type Ia supernovas, we've pushed our vision to billions of light-years away. But do you think this is the end? Not yet. When we reach the end of distance, when even light begins to stretch, redden, and distort, a new measurement method quietly enters: the Hubble constant. This constant, named after astronomy legend Edwin Hubble, not only reveals that the universe is expanding, but has become our ultimate ruler for measuring extremely distant cosmic distances. Speaking of cosmic expansion, this isn't so simple. Going back to 1929, astronomer Hubble discovered a world-shocking phenomenon. Those distant galaxies are all rapidly moving away from us, and the farther the galaxy, the faster it moves. At the time, people thought these galaxies were moving away from each other, but later scientists understood that what we're seeing is the universe itself expanding. This isn't some part getting bigger, but the entire universe's space itself stretching. And no matter where you stand, you see the same expansion speed, like a rubber sheet being uniformly stretched, with every point moving away from every other point. Isn't that a bit incredible? But the amazing part is yet to come. As telescopes became more powerful, scientists discovered a hair-pulling mystery. Different methods for measuring cosmic expansion speed don't match up. For example, the Planck satellite observing microwave background radiation left by the Big Bang measures 67 kilometers per second. The Hubble Space Telescope and Gaia satellite, measuring nearby galaxies, get as high as 73.5 kilometers per second, a difference of 6 kilometers per second. This seems like a small number, but for the entire universe's evolutionary history, it's a big question mark. Behind this speed controversy, there might be blind spots in our understanding of the universe, possibly even heralding new physics to come. But let's not drift too far back to cosmic expansion itself. You can imagine the universe like expanding dough, with galaxies like raisins embedded within. The more the dough rises, the farther apart the raisins become. At this point, scientists use a key clue to track expansion speed. It's called redshift. What is redshift? Listen. Imagine you're standing by the roadside, an ambulance racing toward you with sharp, piercing sirens. But when it roars past, the sound suddenly becomes deep and distant. This sound change is the familiar Doppler effect. When the ambulance rushes toward you, sound waves are compressed, frequency increases, sound becomes sharper. When it moves away, sound waves are stretched, frequency decreases, sound becomes deeper. Light waves are the same. When distant galaxies move away from us, their emitted light is also stretched. Originally bluish light becomes increasingly red. This is redshift. The greater the redshift, the faster the galaxy is moving away from us, meaning it's more distant and ancient. So redshift became astronomers' farthest, most distant ruler, capable of measuring distances to the universe's edge. Remember the Big Bang? That initial cosmic creation fire. Though 13.8 billion years have passed, its afterglow still echoes throughout the universe today. This afterglow is what we call cosmic microwave background radiation today. It's like an omnipresent light mist, quietly permeating every corner of the entire universe. But we can't see it with the naked eye because it's incredibly cold, only minus 270.425 degrees Celsius, just 2.725 degrees above absolute zero. So its energy concentrates in the microwave band of the electromagnetic spectrum, visible only with supersensitive detectors. So where does this cosmic background noise come from? We need to go back to hundreds of thousands of years after the Big Bang. At the moment the universe was born, it was hot and cramped, less than 1/10 its current size. There were no atoms then, only electrons, protons, and photons flying everywhere. The entire universe like a violently boiling particle soup. Especially electrons like restless little reflector plates, making photons bounce around chaotically, unable to travel in straight lines, like light passing through thick fog, unable to see ahead. Until about 380,000 years after the Big Bang, the universe cooled down and hydrogen atoms could finally combine stably. At this point, electrons were incorporated into atoms, and photons finally escaped obstruction, beginning to travel freely through the universe. This time, they were never interrupted again. They are the cosmic microwave background radiation. Every CMB photon we can detect today started from the moment of its last collision with an electron. That moment, we call the last scattering surface, like a baby photo sent to us from the universe's depths. As early as 1948, American cosmologist Ralph Alpher's team predicted its existence, but the people who actually discovered it weren't looking for it at all. In 1965, two engineers at Bell Labs, Penzias and Wilson, were just adjusting a radio antenna but were driven crazy by strange noise. No amount of troubleshooting worked. They even cleaned pigeon droppings. Finally discovering this sound came from every direction in the universe, audible no matter where they looked, even in dark regions between stars. That's right, it wasn't noise, It was the first free light emitted 380,000 years after the universe's birth, crossing 13.8 billion years of space-time to finally reach us. You might think 13.8 billion light-years of travel, so our observable universe's diameter would be 13.8 billion times 2 equals 27.6 billion light-years, right? Wrong, completely wrong, because the universe has been expanding all along. Though this light flew toward us, the places where it was originally emitted have long been pulled to more distant spatial coordinates by cosmic expansion. Recall the Hubble constant we mentioned earlier. It describes the universe's expansion speed. Astronomers calculated that the origin points of these microwave background photons are now as far as 46 billion light-years away. So the entire observable universe's diameter is actually 93 billion light-years. Don't you suddenly feel like we humans in the universe are like dust floating on the Pacific Ocean? But it's precisely these accidental discoveries and precise calculations that let us step by step find our coordinates in the vast universe. You know, in our observable universe, there are as many as 2 trillion galaxies alone. Sounds infinite, right? So if we just wait long enough, can we see farther and farther places until we see through the entire universe? Unfortunately, no, because the universe isn't static, but dominated by a mysterious force called dark energy, which is tearing space itself apart at an astonishing speed. Scientists discovered that those distant high-redshift galaxies are moving away from us at speeds up to 68,700 kilometers per second, twice the speed of light. This means they're escaping our observable range one by one, gradually disappearing from our sight forever. In other words, the universe we can see actually has boundaries. When you look up into the universe's depths, you're not seeing the present, but the past. Because light takes a long time to reach us, the farther the galaxy, the longer it takes. So what we see is actually a historical panorama stretched across 93 billion light-years. But even more shocking, the universe hides a mystery that remains unsolved. Scientists discovered that numerous galaxy clusters are moving toward a fixed direction in the sky, and this direction is unrelated to cosmic expansion. What does this mean? It's like standing on a stretched balloon surface and discovering a wind blowing all the ants on the balloon's surface toward the same point. This mysterious phenomenon is called dark flow. Some researchers speculate that perhaps beyond our observable universe, there's some massive structure we completely don't understand, possibly even another universe fragment. To study this dark flow, scientists focused on the universe's largest celestial monsters, galaxy clusters. They're composed of thousands of galaxies, filled with hot gas that emits X-rays. Researchers observe these X-rays to see how they collide with cosmic microwave background radiation, searching for traces of tiny temperature changes. This microwave temperature disturbance has a special term, the Sunyaev-Zel'dovich effect. You think this is outrageous enough? Then you definitely haven't heard the following theory. Scientists suspect our universe is actually just a giant bubble floating in an energy ocean, and there might be countless such bubbles. These universe bubbles float, collide, and expand like foam, forming a larger system, the multiverse. It's not science fiction fantasy, but natural inference from 2 hardcore theories. First is quantum mechanics, the infinite possibilities we see in the microscopic world. Each possibility might become real in another universe. Second is early cosmic inflation theory. At the universe's birth, it experienced extremely violent expansion, and this inflation might never have stopped, continuously creating new bubble universes beyond the universe. That's right, the universe we're in is very likely just one member of giant bubbles. This bubble is floating in some energy ocean that can't be directly observed. And in this ocean, countless other universe bubbles might be floating. These bubbles might be almost the same as our universe, with galaxies, stars, even life. But they might also be completely different, with different physical laws, numbers of dimensions, even different ways time flows. Doesn't this sound explosive enough? But you know what? We haven't even finished seeing our own bubble. Because light speed is finite, it determines that we can only see places at most 13.8 billion light-years away. This is the boundary of the observable universe. And beyond this, there are more stars, galaxies, and possibly completely different civilizations and matter structures that we can never reach or even communicate with. What we see is just the tip of the cosmic iceberg, And in those unobservable places, perhaps another you is making completely different choices. If you think the universe only starts from one big bang and expands all the way to the end, you might have missed an ancient yet subversive cosmic hypothesis. The universe has been reborn not just once, but countless times. This is the fascinating eternal recurrence, or cosmic cycle theory. Its core idea is simple yet extremely shocking. The universe continuously experiences destruction and rebirth in endless cycles, repeating forever. You can imagine it as one big bang, expansion, stop, big collapse, explosion again, new universe begins. Each cycle is a complete cosmic reincarnation, and the universe we're in now might just be one lifetime among countless universes. This idea is actually older than modern science. In ancient times, people believed the universe would experience infinite cycles of creation, maintenance, destruction, and rebirth, like the sun rising and setting daily, seasonal cycles, life and death alternation. The universe might be a cosmic version of the cycle of life and death. In modern cosmology, this hypothesis has a scientific version called oscillating universe theory. This theory holds that when the universe expands to its limit, gravity will reverse everything. The universe begins contracting, temperature rises, density increases, everything is squeezed back to the starting point like a reverse replay of the Big Bang. Then, at some starting point-like critical moment, a new explosion occurs and the universe restarts. This is called the Big Bounce. Doesn't this sound just like science fiction? But this is a possibility seriously considered by scientists. But the bad news is, as observations of cosmic microwave background radiation become more precise, we find the possibility of cosmic cycles increasingly low. All data points to a colder ending. The universe probably won't collapse or be reborn, but will expand forever until energy is exhausted, falling into complete heat death. A silent, lightless cosmic ending where everything will forever freeze in cold darkness. But don't rush to conclusions. If someday we truly understand dark energy's true nature, perhaps all endings will be rewritten. After all, before the universe, eternity has always been merely the starting point of human imagination. We are like mayflies between heaven and earth, tiny as a grain in the vast ocean, lamenting our brief existence while envying the river's endless flow. The world's most moving great narratives often begin with a journey. This isn't a geographical voyage, but the soul's ultimate inquiry. Who are we? Where do we come from? And where are we going? Since the dawn of recorded civilization, humans have been using stories to explore life's answers. Various civilizations and cultures have woven myths and legends, attempting to touch life's ultimate meaning. And now, in this era where technology and tradition converge, perhaps an entirely new cosmic story is quietly unfolding. This story is rooted in contemporary science, yet also draws nourishment from ancient wisdom. It concerns not only stars and galaxies, but also Earth and you and me. What if the universe truly has its own way of narrating? What if Earth has been whispering all along, but we just haven't learned to listen? In this cosmic story being written, perhaps each of us plays an indispensable role. We can tell the universe's story anywhere. Every piece of land has its unique perspective and voice. When we stand here telling the universe's story, we're reminded that we inhabit a brilliant planet, and we're riding it through this vast, boundless cosmic ocean. This isn't just a story about distant stars. It's also about the ground beneath our feet and our own coordinates in the universe. Next, we'll review together the 13.8 billion-year journey of cosmic evolution. In the scientific community, some call the universe's starting point the Big Bang. That was about 13.8 billion years ago, when everything we know, all stars, galaxies, even the dark matter we can't see, originated from a point of extremely high density and temperature. This starting point contained enormous energy, with early temperatures reaching trillions of degrees. Under the inflation theory framework, in the extremely brief time after the universe's birth, space itself underwent faster-than-light rapid expansion. Starting from microscopic quantum fluctuations, space expanded at exponential rates, laying the foundation for the universe's macroscopic structure. This process wasn't matter moving faster than light, but the geometric expansion of space itself, ultimately beginning the cosmic evolutionary journey that continues today. The universe is continuously expanding, This is one of the most shocking discoveries in human history. In the past, people thought the universe was just a static, unchanging container, a backdrop for all existence. We knew matter changes, but almost no one questioned whether the universe itself might change. Until scientists discovered that the entire universe is changing dramatically. This means the universe isn't an unchanging space, but a living story. It has a beginning and development, and we're living in one of its chapters. And in the distant future, this story might face some kind of ending, though we don't yet know what that conclusion will be. In the 1920s, an astronomer named Edwin Hubble pointed the Hooker telescope at the night sky. At that time, people were still debating whether our Milky Way was the only stellar island in the universe. Hubble attempted to answer this question. His observations not only confirmed countless galaxies beyond the Milky Way, but revealed a shocking fact. These galaxies are moving away from each other, and the farther the galaxy, the faster its recession speed. Hubble's law. This phenomenon indicates that the universe isn't a static eternal stage, but like a continuously stretching rubber sheet, with all galaxies embedded in space-time structure, gradually separating as space itself expands. Starting from Hubble's discovery, humans first realized that the universe has a dynamic evolutionary history. It originated from a violent spatial expansion process about 13.8 billion years ago, with galaxies moving apart as space-time stretched, continuing to this day. Cosmic expansion continues, driven by dark energy, and this expansion is even accelerating. The fine-tuning of cosmic expansion speed is one of modern cosmology's most thought-provoking puzzles. According to the Friedman universe model, the universe's fate is determined by the balance between its density and expansion speed. If expansion speed is slightly below the critical value, the universe might stop expanding due to gravitational dominance and begin contracting. This process would continue for billions of years or more, potentially converging into a high-temperature, high-density starting point. If expansion speed significantly exceeds the critical value, gravitational forces between matter cannot overcome expansion kinetic energy. The universe would rapidly dilute, unable to form galaxies, stars, or even heavy elements, becoming a cold, desolate particle ocean. The fact is, we happen to live in that just right universe, one expanding at exactly the right speed. It allows galaxies to be born, structures to form, and ultimately nurtures life. Though we can't say the early universe had life, everything it displayed seemed like careful preparation for a possibility. The possibility for life to emerge. Physicist Freeman Dyson once contemplated. The more he thought about the early universe's structure, the more he believed that, in some sense, the universe knew from the beginning that life would come. From the moment of the Big Bang, photons began their long journey, crossing about 13.8 billion years of spacetime. Meanwhile, life on Earth underwent 4 billion years of evolution, from single-celled organisms to intelligent civilization, writing another magnificent epic. Until recently, humans finally captured the faint light from cosmic dawn through cosmic microwave background radiation. These primordial photons, released about 380,000 years after the Big Bang, are like time capsules, carrying information about early cosmic density fluctuations, revealing how galactic seeds gradually grew under gravitational influence. They're like time's messengers, silently telling a magnificently vast story, how the universe was born and where we truly come from. You can't help but ask, what gave birth to such a world? And what creative force created such an ordered universe? Think about galaxies, those distant cosmic islands, from spirals to ellipticals to irregular forms. How did they appear? And who arranged their existence? Now we know there are hundreds of billions, even trillions of galaxies in the universe, so vast, so exquisite, so awe-inspiring. And these questions are the starting point for humanity's continuous gazing at the stars and questioning our own origins. Think about our own Milky Way, this massive spiral galaxy with spectacular spiral arms, looking like a flower blooming in the universe. When humans first observed these spiral arms, we thought they were cosmic limbs packed solid with stars. But actually, they're more like a rhythm density waves passing through nebulae. When these density waves pass through interstellar clouds of hydrogen and helium, they're like sparks across dry grass, igniting stellar birth. So rather than calling the Milky Way an object, it's better described as an ongoing activity, a vast and continuous cosmic creation. We live in such an environment, a place full of creativity, nurturing stars and celestial bodies, in the embrace of a galaxy that's always moving in its silence. In ancient times, stars weren't just decorations in the night sky. They were considered living, even sacred beings. People looked up at the starry sky, treating stars as dwelling places of deities. Throughout human history, almost every culture has been awed by the night sky. That solemnity in tranquility, that brilliance in permanence, raises awe in our hearts and awakens endless imagination. We create seasons around stars, arrange migrations, and write myths. Stars not only light up the night, but illuminate the threads of human civilization. They shaped our beliefs, our time, even the order of our entire world. This might be the most touching aspect of the cosmic story. Stars are our ancestors. Every drop of blood in our bodies, every breath we take, can be traced back to those stars burning in the darkness. Stars aren't motionless light bulbs. They're living celestial bodies that are born, grow, and die. When a star is born, it's because a nebula continuously compresses under gravity until its core becomes hot enough to ignite nuclear fusion. Hydrogen fuses into helium in intense heat, releasing enormous energy. This energy pushes outward, achieving a delicate balance with inward-pulling gravity. This is the miracle of stellar existence. But this balance isn't ultimately eternal. When a star exhausts its internal fuel, gravitational collapse dominates, followed by a violent explosion, supernova. The energy it releases can reach 10 to the power of 44 joules, equivalent to hundreds of times the sun's total lifetime radiation. In this cosmic scale nirvana, light elements like carbon and oxygen synthesized in stellar cores, along with heavy elements like gold and uranium produced through supernova shockwaves or neutron star mergers, are all ejected into interstellar space, becoming material for nurturing new stellar systems. These interstellar materials gather again under gravity. New stars are born from nebulae, planets form around stars, and life seeds quietly sprout in suitable environments. Therefore, we're not just observers gazing at the starry sky, but direct descendants of the stars. Every carbon atom in our bodies has been tempered by nuclear fusion in stellar furnaces. The calcium forming our bones, the iron in our blood, even the sodium and potassium ions transmitting signals in our synapses were all reborn in supernova explosion shockwaves. This is the cosmic poetry revealed by science. We don't stand upon dust, but are woven from stellar ashes. Stellar death and rebirth isn't just a cycle of celestial evolution, but the ultimate answer to how life can exist across billions of years of spacetime. Imagine the sun hanging high in the sky, burning quietly, but actually every second it converts 4 million tons of mass into energy, like a tireless nuclear engine providing continuous power to the entire solar system. This isn't simple burning, but an exquisitely refined nuclear reaction supporting wind, rain, light, heat, and all our life activities. Early humans couldn't understand it and could only worship the sun as a deity. But today we know our planet, our bodies, even our consciousness all depend on its continuously roaring nuclear heart. What's shocking is that all this started from just an unremarkable dust cloud. For humans to truly realize we live on a planet orbiting a star wasn't easy. This concept was once extremely foreign, even difficult to accept. So where should life's story begin? How did it start? Honestly, we don't have a definitive answer yet. But this doesn't mean we know nothing. In the past, people thought the universe was like a cold machine, with life just a byproduct of some accidental collision. In other words, life isn't accidental. It's more like an inevitability. When a planet's matter reaches a certain critical complexity, life's flower naturally blooms in this soil. Imagine a whirlpool. As long as there's flowing water, it can appear. But wonderfully, a whirlpool isn't specific water molecules spinning in circles, but a dynamic structure formed by water molecule movement continuing. Old molecules leave, new molecules replenish. What truly persists is the spinning pattern. This is what scientists call emergent structure, a holistic order spontaneously formed by simple components through local interactions. Now applying this logic to the universe, Scientists speculate that the Big Bang 13.8 billion years ago wasn't simple energy eruption, but rapid expansion of space itself. During inflation, quantum fluctuations were amplified into tiny differences in matter density, which gradually collapsed under gravity to form galaxy clusters, stars, planets, and other structures. This process is like cosmic self-organization, from uniform plasma to complex celestial systems, with physical laws driving evolution from disorder to order. This isn't ordinary energy, nor merely life energy. Some scientists believe this is a kind of conscious energy. Yes, more and more biologists are beginning to speculate that consciousness isn't exclusively human, but that seeds might have been planted from the universe's self-organization from the very beginning. The universe's creativity didn't stop at stars. It continues unfolding with every complex upgrade of life. After orbiting the sun for hundreds of millions of years, life on Earth finally learned to resonate with the sun. Some of the earliest life forms evolved molecules that could receive sunlight, beginning to absorb light and convert sunlight into food. This was the birth of photosynthesis. As life became increasingly complex, a wonderful phenomenon quietly emerged: entanglement. Not quantum entanglement, but organisms connecting and depending on each other, you in me, me in you. The more complex life becomes, the tighter the connections. The entire Earth began like a polyphonic symphony, with every organism as one of its melodies. In the past few hundred years, we've learned more about Earth than in the previous 100,000 years. We finally understand that Earth isn't a backdrop. It's not a platform where life is placed. Life was never an appendage. Life is part of Earth. Life has a partnership relationship with oceans, atmosphere, and land. You know, our air contains 21% oxygen. This is unique among all known planets. And the only reason we can breathe oxygen is that life on Earth produces it every day. That's right, air isn't a gift from nature, it's a gift from life. So we can say that air contains life's echo. Every breath you take is actually an interaction with all life on Earth. From this perspective, our lungs are connected to the entire planet. Perhaps Earth isn't just a complete system. It might truly be maintaining life's prosperity in its own way. You know, the temperature range where life can exist is actually extremely narrow. But surprisingly, Earth has maintained this narrow temperature band for 4 billion years. Initially, scientists thought this was just because Earth's habitability came only from its distance to the sun. Just coincidentally, just right. But later in the 1950s, we discovered something world-shocking. The sun's temperature has actually increased by over 30% in these 4.6 billion years. This is outrageous. Logically, Earth should have overheated long ago. So why are we still here? Did Earth adjust its own air conditioning? We discovered that in early Earth's atmosphere, carbon dioxide concentration was 100 to 1,000 times today's levels. So where did all this carbon dioxide go? The answer is, Earth quietly cleaned it up. Ocean algae used them to make shells. Then when these algae died and sank to the seafloor, carbon dioxide was sequestered. Thus, as the sun got hotter, Earth slowly cooled through this mechanism. Doesn't this sound like the entire Earth regulating temperature for life? If this is true, then the atmosphere isn't just air, it's like a living membrane. Each of us doesn't just live on this planet, we're part of this vast and complex system. What's the most amazing thing about living cells? They can continuously learn through time. This is why life is completely different from other early non-living things. Think about a star, it can continuously self-organize and exist for billions of years, but it never needs to learn anything. It doesn't need to adapt or change. And life continuously changes itself to adapt to new environments and new challenges. Even more amazingly, life preserves all these experiences through DNA. In other words, every cell contains the power of memory, allowing life to learn, grow, and evolve. We learn mainly through our senses, and life has invented countless ways of perceiving. This creative process continues. Billions of years ago, the earliest cells became light-sensitive, able to perceive light and even move toward it. This ability eventually evolved into eyes. We have fossil evidence that about 500 million years ago, trilobites evolved eyes made of calcite. This primitive vision was super successful. the compound eyes of flies and lobsters still retain its form. Another type of eye was developed by fish, the eyes we're most familiar with because we inherited these aquatic eyes. Even after 500 million years, vision is still evolving. In humans, vision gained a new skill. Insight became more powerful. After billions of years of biological evolution, a complex cognitive phenomenon emerged in life systems: consciousness. With this new observational power, we blink in that mysterious yet dazzling light, occupying an ordinary yet unique node in the universe's space-time network. When we open our eyes, everything we see is brand new, each burning with the universe's flame, carrying billions of years of history. For a rabbit, an eagle is a predator wearing a mask of destruction. But in this relationship, eagles forge sharper vision while rabbits develop swifter escape techniques. From pain and death, an ecology of interdependence and symbiosis is born. In cruelty, life blooms with endless wisdom and resilience. Our human origins can be traced back to about 13.8 billion years ago at the universe's birth. The Big Bang produced light elements like hydrogen and helium. Then stellar furnaces synthesized heavy elements like carbon, oxygen, and iron through nuclear fusion. Supernovas scattered these stellar materials into interstellar space. 4.6 billion years ago, stellar materials converged to form Earth, where carbon-based molecules in primordial oceans underwent billions of years of chemical evolution, forming the first life cell 3.8 billion years ago. From that moment, all organisms became genetic distant relatives through genetic material continuation, sharing the same DNA coding system. In vertebrate evolution's long river, the primate lineage underwent key divergence about 6 million years ago, one branch toward chimpanzee evolution, another beginning our human ancestors' unique journey. The earliest hominid members began attempting upright walking, freeing forelimbs to use tools. Through stages including Australopithecus, Homo habilis, and Homo erectus, the human brain's prefrontal cortex tripled in size over 2 million years, forming complex neural synaptic networks. This structure enables us to engage in abstract thinking, construct symbolic systems, and elevate real experience into dreams and imagination. In primate evolution, natural selection gradually extended developmental cycles, making human ancestors retain more juvenile characteristics. Compared to chimpanzees, our childhood is not only longer but develops at a slower pace. For example, human brain synaptic pruning continues until adolescence, while chimpanzees basically complete it before age 5. To understand what makes humans human, observe any mammalian young. They jump, play, explore the world with eyes and mouths, simple, pure life bringing infinite excitement. These behaviors reveal some essence of freedom. After nearly 4 billion years of evolution, a form of life capable of maintaining a state of freedom appeared. They're spontaneous, curious, flexible, open, driven by inner forces to try everything unknown. Humans aren't just products of evolution, but consciously participated in their own birth. To me, this means the birth of a species capable of changing planets. This change spans the entire planet, unfolding confidently and efficiently in every civilization, erupting like echoes from those symbols. We're beginning to understand the universe's profound forces, the very forces that gave birth to galaxies, stars, and life itself. Perhaps the universe is slowly unfolding toward some entirely new destiny. If our ultimate goal is to deeply experience this vast universe, then we'll gradually realize that in some sense, we are the universe's mind and soul. Our deepest journey is wholeheartedly participating in this cosmic prosperity and evolution. As we float in this mysterious vastness, is there a depth that can help us regulate consciousness, harmoniously resonating with the universe's evolutionary rhythm? Miracles will guide us, and humanity as a species is easily amazed and moved by all phenomena in the universe. The universe's body gave birth to our bodies. The universe's self-organizing dynamics gave birth to our souls. We belong here and have never left. These profound scientific discoveries are leading the universe to write new stories. When we stand in time's long river, looking back at 13.8 billion years of cosmic history, the answers have long been written in the folds of stars. We are love poems the universe wrote to itself, echoes after stellar burning, notes dancing in planetary pulsations. From the moment of origin's explosion to the instant of cellular birth, from the first starlight crossing primordial chaos to humanity's first gaze at the firmament, the universe has never stopped breathing creation, and we are the most subtle tremor in this breath. The story never ends, because the universe's poem is still being written. In our eyes gazing at the starry sky, in our steps exploring the unknown, in our tenderness protecting life. The next miracle might be hidden in a child's gaze toward the Milky Way, in data flickering in laboratories, in humanity's courage to walk hand in hand toward the stars. This is our cosmic story, not a cold accumulation of matter, but a collaborative creation spanning billions of years. We were once stars, and in the future will become co-dancers in cosmic evolution. When we learn to breathe in sync with galaxies and dance to quantum rhythms, we finally understand that life's ultimate meaning isn't in seeking answers, but in becoming the answer itself, becoming the universe's way of loving itself, becoming the light of awakening that never extinguishes in eternity.